Okay, this one is the worksheet about energy, but I decided that I would build on the worksheet that we did last week about projectile motion, and just use the same example, but look at the energy of what's happening rather than the velocities and accelerations and times and so on. So first up, we've got a 20 gram mass of the arrow. So while we're summarizing, mass is 20 grams, but let's work in proper SI units, 0.02 kilogram. Always important to go straight to the SI units. We have its initial kinetic energy, or its initial velocity. This is U overall at 23 degrees, so 56.7 meters per second. But that's just its velocity. That's its initial velocity at least. So to find, for part one, to find its kinetic energy, we know EK equals a half mv squared equals a half times 0.02 times 56.7 squared equals 32.1 joules. That's the kinetic energy that it has when it leaves the arrow, leaves the bow. So that's the energy that we're starting with. Now, overall, that might be transformed, but it's probably not going to be added to. We don't have a rocket-propelled arrow, so that energy that we started out with is probably what we're going to be working with for the rest of the problem. That seems plausible, at least. We'll test that intuition later. Now we can find its gravitational potential energy at the top of its flight. So it is, this is question number 2, gravitational potential energy. Well, we have a formula for that too. EP equals mgh equals the mass, 0.02 kilogram, times g, the acceleration due to gravity, 9.8 meters per second squared, or newtons per kilogram. The two units are actually interchangeable, and which one we use depends on what we're trying to do, but it's the same thing, times the height, which was 25.14 meters we calculated in the last problem, and overall that's going to be 4.9 joules. So at that point, we've converted some of the energy from the initial velocity into position within a gravitational field, so that it has gravitational potential energy because of where it is in the gravitational field. Okay, so kinetic energy at the top of its arc. Now, we know that the horizontal velocity, and this is actually harking back to the projectile motion. The horizontal velocity started out as 52.2 meters per second and stayed the same the whole time. So that means the horizontal velocity will still be 52.2 meters per second at the top of the motion. So we can work out the kinetic energy now. So we just worked out the kinetic energy when it left the bow. We worked out that it used some of that energy to gain position. What's the kinetic energy now at the top of its flight? Half mv squared again, but with the same m, different v. A half times 0.02 again, but times 52.2 squared this time, is equal to 27.2 joules. That's the kinetic energy at the top. So we started out with 32.1, and we ended up with 27.2. If you add that to the 4.9, you should find that it gives the 32.1. So in other words, all we've done is convert some energy from one form to another. Energy hasn't been created or destroyed. We've converted some of the kinetic energy into potential energy at the top of the motion. Okay, and they do. I think they actually do accurately, at least within rounding error if we've rounded anything off. And sorry, before I make it disappear, question 4, if the bow was pulled back 25 centimeters, find its spring constant. So the spring constant is a measure of the spring potential energy. So before it had an initial velocity of 56.7 meters per second. It had the energy stored as energy in the bow, the bending of the bow. So for that, we can use another equation, which we know, I'm just going to call it spring potential. I'm not sure what subscripts I've used, but the spring potential energy, the equation is a half kx squared, where k is the spring constant, which is what we're actually looking for, and x is the displacement, the distance that the spring is distorted. So in this case, the distance that the bow is pulled back. So again, we want to go from centimeters, which we were given, into the SI unit, so 0.23 meters is the actual displacement. Let's rearrange that to make k the subject. So k equals 2 ESP over x squared. I did that algebra without doing the intervening steps, but you can kind of work through doing the same thing to both sides and you'll discover that that's what it ends up equaling. So if we substitute in the relevant values for that, we'll get 2 times. Now, that spring potential was just converted into the initial kinetic energy up here, 32.1 joule. So we can just use that 32.1 joule. Right, so all of the spring potential turned into the kinetic energy at the beginning of the flight over, it was 20, did I say 25 centimeters? I'm sorry, and I wrote 23 here. Apologies if that was confusing. 25 centimeters. So 0.25 meters. And that has to be squared, because it's x squared. And if we do the calculation, we get 1027.2. And the units of spring constant are newtons per meter, because it's a force of that many newtons to pull it back for every meter that you pull it back. So that's a sensible unit for that. So that's the spring constant of the bow is 1027.2 newtons per meter.